A standard desktop computer is designed for a specific scope, handling the routine, everyday tasks of a single user. To execute these commands, the architecture relies on a single central processor to carry out instructions one after another. We typically measure the speed of this processing in MIPS, or million instructions per second, and electrical resistance make further speed increases impossible. To solve problems that exist beyond this threshold, we cannot simply rely on faster chips. We have to rethink the way a computer is built. Many of the challenges we face today involve variables at a global scale, such as the long-term modeling of the Earth's climate. Other fields, like astrophysics, require us to calculate the evolution of the entire universe or track the behavior of dark matter. Processing these massive data sets through a standard single-processor system would take centuries to reach a conclusion. This bottleneck also impacts the development of generative AI, which requires vast amounts of computational power to train complex neural networks. These reality-scale problems create a computational demand that traditional computer architecture is mathematically unable to meet. The supercomputer was developed as the specific architectural solution for these intensive mathematical problems. Instead of relying on the linear speed of one processor, these systems utilize parallel processing. This involves connecting tens of thousands or even millions of individual processors to work together simultaneously. By breaking a massive calculation into countless smaller parts, the system can process every piece of the problem at the exact same time. The strength of a supercomputer comes from this collective power, the ability to coordinate millions of chips to function as a single unit. At this scale, we no longer measure speed in instructions. We use flops, floating point operations per second. Managing millions of processors requires a massive physical footprint, often filling entire floors of a data center. The specialized hardware and high energy demands mean these facilities often cost hundreds of millions of dollars to build. This concentration of processing power draws an immense amount of electricity, which generates extreme levels of heat. As seen in this industrial cooling array, managing that heat requires an infrastructure almost as complex as the computer itself. A supercomputer is less like a piece of office equipment and more like an industrial facility designed to sustain high-level mathematics. Today, the search for higher performance has led to the exascale era of computing. This threshold is reached when a machine can perform 1 quintillion floating point operations per second, known as 1 exaflop. Systems like Japan's Fugaku have pushed these boundaries, using this massive capacity for advanced medical research and scientific modeling. At Oak Ridge National Laboratory, the Frontier system became the first recognized exascale supercomputer in the world. Reaching this level of performance provides the processing headroom necessary to model complex physical interactions with a high degree of precision. In aerospace design, exascale power allows engineers to run virtual aerodynamic simulations that account for millions of data points. These digital models are accurate enough to replace the need for physical wind tunnels, allowing designs to be tested and refined entirely within the machine. In molecular biology, supercomputers simulate the intricate ways proteins fold, helping researchers develop new pharmaceuticals for complex diseases. This satellite data of a hurricane is used by these systems to model the Earth's atmosphere, increasing storm tracking accuracy. By reaching the exascale, supercomputers have become our primary simulation engines, tools that allow us to accurately model and predict the future of the physical world.